Hi, AppSec engineers. In this video, I'm going to be exploring the fundamental API security vulnerability, which is called BOLA. Let's get started with understanding what we're going to be exploring today. We are going to be exploring broken object level access control or broken object level authorization, which is one of the most pernicious API security flaws that you typically find with a lot of REST APIs and generally web APIs all over the world. In fact, it's been a very common vulnerability that you see with multiple providers. You've seen Peloton vulnerable to it. You've seen Coursera vulnerable to it. You've seen Echelon vulnerable to it. You've seen a bunch of apps being vulnerable to it. So this is something that we're going to be exploring in this particular video, and we're going to be looking at a lab and an example around how this vulnerability actually works. Let's get started. Now, broken object level authorization or broken object level access control is something that I'm sure many of you or most of you would have seen in an application or the other. So let's take an example of a banking application, right? Now, if we take an example of this banking application, now let's say you have an operation that looks like this. That says www.bank.com/getstatement.jsp ID is equal to 1001, right? Now, if I change, so this basically, as you can imagine, when you access this particular URL as an authenticated user, it will give you access to your statement and you are ID 1001. However, if you change this ID value to 1002 or 1003, do you get access to somebody else's statement? I'm sure you've started to realize that, oh my God, I've actually seen this happen in several applications, and I've seen this probably in my own application. So this is a pretty common flaw, and it happens all the time. And with APIs, this kind of flaw kind of becomes a little bit more pernicious because we see a lot more with APIs. Now, this is essentially called broken object level authorization, simply because you are directly accessing a particular object. In this case, you're referring to that object by the primary key, in this case 1001. And by tampering with that object reference value, which is 1002, 1003, essentially incrementing or changing the object reference value, you are essentially gaining access to somebody else's records, right? So you might get access to somebody else's bank statement, or you might get access to somebody else's credit card number, or you might get access to somebody else's personally identifiable information. And from there, you may be able to gain access to a completely different set of privileges. So the idea here is that you are bypassing the authorization that the system should have had when referring to these object references. And that's basically what BOLA is all about. And in common terms or in previous terms, I think when I started working in application security, this used to be called insecure direct object reference, which is also called IDOR. So IDOR and BOLA are pretty much the same thing. Just that with APIs, I think they wanted to call it out as a slightly separate item, which is called broken object level access control, because with APIs, all you're doing is essentially referring to a lot of objects and you're accessing them through the APIs and through some of the parameters provided by that particular API. So we're going to be seeing how we can compromise broken object level access control, and finally, how you can actually go about fixing it. This is very important, right? Just compromising it is pointless. You have to figure out how to fix it. And with BOLA, the fixes are pretty deep and pretty ingrained. So we're going to be looking at all of these things in the upcoming part of this video. Stay tuned and let's get started. If you're new to this channel, I highly recommend that you like this video. And if you like content around application security, Kubernetes security, cloud security, DevSecOps, and anything latest and greatest in the field of application security, you should be following this channel. So definitely click on that subscribe button and let's get started. Aside from that, we're also on Twitter, on LinkedIn, on Instagram, and on Facebook. Do check us out. Share our channel, give us some love, and help us create more videos like this that can help you become a better AppSec engineer. We're going to be looking at the primary key variant of insecure direct object reference, and we'll be looking at two sides of this lab. We'll be looking at both the attack or the vulnerable side of this lab, and we'll also be looking at a defensive side of this lab where the problem has been identified and fixed, right? So as always, let's get started. We're going to open up a terminal window to run our commands. Now this application that we're running is an API. So we're going to be running this in multiple terminals, right? So the first thing we're going to do is we're going to deploy this application. It's a very simple Python application that we're going to deploy. And we're going to get started by running our application. Now this is an API, which is a single file. And we're going to be using an SQLite database to actually store the data from this application. Okay, so the application, as always, is available in the root directory, and we have a small SQLite database file that we're using to get started. Now, the first thing I'm going to do is I'm going to just quickly minimize this, open up another terminal. I'm going to pin it on the top panel here and get started. So the lab is pretty simple. The way it works is that you add yourself as a user to this application. So you invoke something called a create user. You log in and you create your credit card number on the application, right? So you create a card number on the application. Now, the way it should work, obviously, is that only you should be able to access your credit card, right? Somebody else should not be able to get access to your credit card information. However, through an insecure direct object reference flaw, you will find that this is not necessarily true. So let's look at this and see how we can actually perform this particular attack. So I'm going to walk you through the attack as I'm running it, and then you can see what I'm talking about. So the first thing we're going to do is create a user. So we're going to make a post request, and we're going to add ourselves as a user to this application. So create user, and I'm going to call this user at corp.com. Password is equal to hello1234, right? Some password. You can, whatever password you want, you can choose. So it creates a new user, as you can see. Now I'm going to log in as the same user. Localhost 5000, login, email, user at corp.com, password hello1234. When I log in, I have successfully logged in, and I've got an authentication authorization token here. I'm going to copy this token, and I'm going to store it as an environment variable called uToken. So uToken for user token. And I'm going to store this token in that particular variable so that I can reuse it in subsequent requests, right? So now I'm going to create a credit card number for myself. Since I'm the user, I'm creating a credit card number for myself. And since I'm using my authentication token, it's going to bind it to my account, right? So HTTP post, HTTP localhost 5000 create card email. I don't need the email in this case. I'm just going to put in the authorization token, which is $uToken. Remember, we stored the token as an environment variable, so we're going to just use that same token. Now I'm going to generate a card number. I'm just going to use the Visa test card number, which is 4111 1111 1111 1111. That's the Visa test card number. I'm going to give it a CVV value of something. It doesn't have to be something real. I'm just going to give it 211, and I'm going to give it an expiration date of 12/24. Right, so this is the card I'm creating for myself. The card has obviously been created for me, and this card is successfully created. So now if I go in and look at the cards, or all my cards, right? So I get HTTP localhost. So I have another route that allows me to retrieve my cards. So if I do get cards, and if I put in my email, user at corp.com with the authorization header of uToken, you will see that it gives me my card number back. So if I add another card number to my account, it's going to give me the other card number in my account as well. Now the idea here is for the attacker, who is also another user of this application, to be able to gain access to your card number. So you're the user, you've created 4111 whatever card number. The attacker wants to be able to gain access to your card information, and that's what the attacker wants to do. So let's simulate that condition. So let's sign up as the attacker. So I'm going to sign up as another user. I'm going to create user, I'm going to say email attacker@corp.com. This is just another user I'm creating. Hello123 is the password, and I'm creating that user. Now I'm going to log in as that user. HTTP post localhost 5000 login email attacker@corp.com password hello123. Now when I log in, I am obviously going to get a token. I'm going to copy this token, and I'm going to create another variable from it called a token, and I'm going to paste this variable in there. Now, obviously, when I try to retrieve my card numbers, I don't get anything back. So if you see the previous one, as the user, when I retrieved, the previous user retrieved his card numbers, in this case, you see that you got this particular card number. Now, if me, as the attacker user, if I use the a token, my token, if I authenticate and use this particular token, let's see what I retrieve, right? So it's again HTTP GET, HTTP localhost get cards attacker@corp.com. Authorization is the a token, or the attacker's token. If I see this, you don't get anything because I don't have a card number associated with me. Now, but there is another URL called get card, and you can take an ID. That particular URL takes an ID, and that's where the developer has not done a good job of managing permissions. So let's use that URL and see what you can do. So you see that by get card, and I'm going to pass an ID of 1. Okay, so I'm just assuming, as an attacker, I'm assuming that there is a card, a number with a primary key value of 1, right? So I'm assuming that, and I'm saying, give me the primary key value 1. I'm still going to pass in my attacker token, so which means that I should not get anything back, right? Because I don't have any card numbers associated with me. But if I do this, you will see that it gives me somebody else's card number, because at ID 1, there happens to be a card number present, there happens to be a card object present, and this particular function, the get card function, we're not checking the permissions for effectively. As a result, the attacker is going to be able to do things like just substitute this 1 for another primary key value, and if it's a large enough system, you can see that the attacker is going to be continuously be able to increment the value and completely gain access to user information that the attacker should not have access to. So as you can see, insecure direct object reference is a classic authorization bypass attack, where the attacker uses either URL parameters or JSON parameters or any of these parameters to be able to bypass the authorization. So the attacker is relying on some weak authorization checks and the primary key values to be able to increment and figure this out as he or she is going along with the attack. We saw how we could leverage the attack of insecure direct object reference, where we could increment the primary key values, like in this case with the credit card number, and we were able to gain or access credit card numbers that did not belong to us, right? Did not belong to. So as the attacker, I was able to completely enumerate these values and gain access to credit card information that was not even mine. So that's how the attack actually happened. But let's see what really led to the attack and how it was eventually fixed. So before we look into the code, let's look at the secure variant of the same example. So what I'm going to do is I'm going to stop this. I'm going to clear screen. What I'm doing here is I'm essentially stopping the server process, and I'm going to start another variant of the same application, which we call the secure app. So we have an app and we have a secure app. That's what we're doing in this case, okay? So we're going to start, instead of starting app.py, I'm going to start secure_app.py, and it's going to do the same thing. It's going to start up another instance of the application, except that this app, the secure app, obviously has the authorization check to do that. So previously, just to recall what I did, I signed up as a user, I logged into my user account, I created my credit card, and I was able to access my credit card as the user. Now the attacker, who's also a user of the application, what the attacker did was that the attacker signed up as a user, logged in, but using the get card API endpoint, the attacker was able to gain access to even the card that did not belong to the attacker. So in this case, card number 1 did not belong to the attacker, but still, because there was not any kind of validation or authorization check done, the attacker was able to gain access to that. So let's try and get the same card number again. Now, remember, we're running a secure instance of the application, so this should not be possible now. So when I do this, remember, I'm again accessing the get card ID 1 with an authorization token of the attacker's authorization token. So I'm sending the attacker's credentials or the authorization token to the application. Let's see whether it works. And you see that the attacker, there was no card number retrieved because the attacker does not have any card number associated with their account. So you will see that clearly, if I access this card number as the legitimate user, if I use the user's authorization token, you will see that it's retrieved. But if I access the same record with the attacker's token, you will see that the attacker is not able to do it, because clearly the application is binding the privileges of that particular card number to that specific user. Remember, the use case is that I am the user, I should have access to my cards. That's it. Nobody else should have access to my cards. So what it should clearly do, the permissions that should be enforced is that, hey, check if this user is the owner or is the creator of this card, and if yes, only then allow access to that particular user to access that card number. So you can see that this version of the application is much more secure than the previous variant of the application. And I'm going to quickly take you through a tour of the code itself. And let's look at the get cards function in both the insecure and the secure version of the application. Right? So when you look at the get card function, not get cards is also a function, but we're not looking at that. That's fine. But if you look at the get card function, and we're looking at this in app.py, so this is the insecure version of the same application, right? So if you look at the get card function, you will see that so we're essentially getting the card ID that we want. It's only checking if the user is a authenticated user of the application, and then it's essentially just giving the user whatever card ID the user requests. So in this case, it just checks, hey, get me all the payment cards where the payment card ID is equal to the card ID that is passed in the URL parameter. So if it happens to be a legitimate ID, it just gives you the response with that particular information about that card and the card number and the CVV and all of that stuff associated with that card, right? So in this case, there is really no authorization check being done. So it just checks, hey, is it a legitimate user? Which again, it should not be possible, because remember, the attacker in this case is the user. So it just checks whether it's a legitimate user with the authorization token, and we are essentially checking whether the ID that has been passed from the user in this case is the same as one of the IDs that already exists in the database, and if it is, it's just going to give you the payment card information related to that card ID. Now this is insecure because it should be checking whether this ID is matching, as well as whether the ID or the card belongs to that particular user at all in the first place. Only then it should return a positive response, otherwise it should not return anything. Now let's look at the secure variant of the same example. And let's look at the code in that variant, which is pretty much the same. The only difference here is that the first thing we're doing is we're getting the authentication token from the user. We're checking whether a user like that exists. And this is the real important line. Line number 201 is the critical line that is securing our payment cards, right? So we're first checking whether the ID is the same as the ID passed in the URL request, which is what we were doing before as well. Nothing new here. But the second thing we're doing is we're checking whether the user that authenticated in this request is the same as the user on that credit card. If both those details match, only then we're returning a response. Otherwise, we're returning a does not exist, right? So in this case, it's a very simplistic authorization system, but it's an effective one nevertheless, because the developer is ensuring that the payment card ID is the same as the one passed, and the one that is being requested by the user belongs to that particular user. Only then the details are being retrieved and given to the particular user, as a result making it a much more secure alternative from the previous example. If you like that video, I highly encourage you to click that like button. And if you like content like this and you want to be reminded of more of this content from our channel, I highly encourage you to click on that subscribe button so that you can never miss a video from AppSecEngineer. That's it for now. Thank you very much.